we are very glad to have Mihai Putinar deliver his final talk in his stay here. That's the Eigenfunction seminar. It's on algebraic positivity and analytic positivity.
Thank you very much. Thank you for hospitality, for the invitation. It was a unique opportunity to review old and new material and to rearrange it into a format which is, I think, accessible to non-experts. What I'm talking about is the relation between algebraic positivity, as you can imagine, and many aspects, how it enters into analytic positivity. And I'll start with a very basic question. Why is cosine of theta less than 1? Everyone has an opinion about it. There is geometric, but I prefer the following proof. 2 times 1 minus cosine theta is 1 minus cosine theta square plus sine theta square. You see it immediately. So rather than evaluating the function at every point and checking its positivity, or invoking a geometric argument, we have a frozen formula, an algebraic identity, which we'll call it today certificate of positivity, which gives you for free, or not for free, a little work, but in one shot, the non-negativity of this quantity. So that's the theme of my work today. We relate positivity first to completing squares, to sums of squares. And there is a saying that all elementary inequalities you know in mathematics are obtained by completing squares. Please review this if you if you want to contest. And a second approach to this question, if we are in Euclidean space, let's say x and y are in some real Euclidean space, we have the Cauchy-Schwarz inequality, which is essentially the cosine inequality. So I propose the following proof. Let's take x minus the projection on this vector on the y direction. Certainly, this vector minus the projection on the other direction is greater than 0. And if I expand, I get x squared, the mixed terms twice, plus xy squared. The norm square over this square is y squared. So this is not the textbook proof of Cauchy-Schwarz inequality. But again, it is encoded into this single square positivity. I speak loud, is enough?
Yeah.
Okay. So I dismantle this instrument.
Can we take out the mic? Oh, this is recording. So this is recorded.
The other one, the recording is working. So one more time, we have two instances almost of the same inequality obtained by looking at a square as an universal non-negative element. And that's the theme of the first part of my talk. Then we'll use this to relate to analytic questions, and almost everything what I'm touching today has to do with such observations. Some of them are elementary. I apologize if you're not here. Some of them relate to my previous seminar talks this week, but I'll make it accessible and easy to understand. So let's go back. Hardy.
I have a quick question.
Yes, please.
There are some major inequalities that cannot be proved like this, right? I mean,
Of course there are.
but no, including like the triangle inequality can be proven.
I'll arrive there a little later. Hardy, you know, he wrote with the right textbook on number theory, very beautiful, and he claims that the representation of an integer as a sum of squares is one of the most celebrated problems in the history of numbers. And he traces this back. He wrote the whole count, goes to Diophantus, Girard, and so on. And this theme in number theory to represent primes or not as sums of squares continues even today to be of interest. So I jump a little, and I'll show you the touch of Minkowski, the young Minkowski, the doctoral student, under the mentorship of Hilbert. So already was known at that time that every integer is a sum of 4 squares. That was Lagrange, major achievement. And the Academy in Paris in this year, 81, is asking, okay, if we have a sum of 5 squares, how many different ways you can write an integer into 5 squares? And Minkowski, the 17-year-old Minkowski, got the prize of the Paris Academy solving this question, which turned out to later to be his PhD dissertation. And he relates this to Gauss, to the theory of quadratic forms. And he makes this very short comment. I'll not go into the details here, that looking at quadratic forms of 4 variables will give you a hint into how many ways you can decompose an integer into 5 squares and so on. So this is 1885, Königsberg. The student Minkowski under Hilbert is defending his thesis, published no more no less, so remark that he is a very young scholar in Acta Mathematica. And inserted there in somewhere in the middle of the discourses, it is not probable that every positive form can be represented as a sum of squares. So he passes from numbers to forms, to polynomials, and is asking exactly this question, and has a hint that this may not be true. Hilbert supported this with a complete proof. So the year is 88. And contrary to what is happening in one direction, Hilbert showed that in 2D, not every non-negative form is a sum of squares. So I'll give you a little hint of his reasoning. Let's prove it together in one variable. That's an exercise for your students. Suppose that a polynomial with real coefficients is non-negative on the whole axis. I decompose it over the complex field, and I have the real roots. If it is non-negative, they have to be even order. And I have the complex roots, but the complex roots produce each 2 squares, complex conjugates. We multiply them all, and we have a big number of squares. And here comes Lagrange with the following beautiful identity, which again is a good exercise for your students. If you take a product of 2 squares, it can be rearranged into a sum of only 2 squares. Simply beautiful. Once you see it, you can do it. But the question is, how? And if you just think a little of complex variables, here is the multiplicativity of the modulus of a complex number. So a very sleek, a very quick proof of this identity. Now, once you have it, it's algebraic. You don't have to go over real numbers. So in particular, any polynomial, which is non-negative on the real line, is a sum of 2 squares. Now, the construction of Hilbert was rather intricate, was in the line of projective geometry as was developed at that time, and is non-constructive. Thank you. I'm empowered with 2. I was raised in rank. So, take 2 cubics. We speak about the real affine space here, but in general, this works over the projective 2-dimensional space. Take 2 cubics, which intersects transversally in 9 points. And there is a famous observation of Schall, the founder of projective geometry, saying that in this situation, if you take a polynomial of degree 3 vanishing at 8 of these points, automatically would vanish at the 9th point. This is called today the Cayley-Bacharach theorem. It's not totally trivial, but at least for low degree, for conics and for cubics, you can do it with linear algebra. So this is rather elementary. And then he argues as follows. Let's consider a polynomial non-negative on the plane, degree 6, which vanishes at the 8 points, but is strictly positive at the 9th one. Everywhere non-negative. And he argues that this is possible to find. Then, if this is a sum of squares, notice that the degrees of these sums each is 3 or less, and will vanish at the 9th point. So, Hilbert showed it, but there was no example around, believe it or not, for 80 years. And from this observation, Hilbert derives his famous 17th problem. Okay, a polynomial of 2 variables, non-negative, is not a sum of squares. Is it possible to write it as with denominators, as a sum of squares of rational functions? And that was his 17th problem. This resisted for quite a while. It's one of the Hilbert problems, quite famous. And it led to the field of real algebra and real algebraic geometry as we know it today. Now, in the same time, Hilbert moves on different tracks, as you know. He solved the Waring problem, also decomposition of integers, by passing, that's the point I want to make, to an identity of forms in 5 variables here, by integrating them over the unit ball. in 5 variables. Why it is important here? Because we arrange these sums of squares to the power m in a sum of 2m squares in an average. Oh, sorry. And in the same time, he studies mathematical physics, as you know, and he wrote this very foundational book on what we call now Hilbert space, on integral equations and the spectral theory, as we call it today in modern terminology. And the whole background was that the spectral analysis, as you study vibration of strings and I don't know, evolution of dynamical systems, requires infinitely many squares, requires a positivity which goes beyond numbers. Namely, you have what is a Hilbert space, is a sum of squares in the end, the inner product, and requires decompositions into sums of squares. These are just the spectral decomposition of, let's say, quadratic form in infinitely many variables. So somehow in the air was parallel to the number theory, this idea of developing quadratic forms of infinitely many variables and decomposing them into sums of squares for very practical purposes, for vibration of strings, for instance. And here is the major observation I want you to be aware. And probably you don't see it in the textbooks. You all passed and study the spectral theorem for self-adjoint transformations. Take a linear bounded self-adjoint operator, what we call today on a Hilbert space. The statement is the following. If we take a polynomial, which is non-negative on the line, and we apply it to the operator, this is non-negative in the Hilbert space sense as a linear transformation. Highly non-trivial. You have an infinite matrix, you have a non-negative polynomial. Why it is so? Well, simply because if this is a sum of squares, at the level of the functional calculus for operators, this decomposes. And as you know, each of the factors, we have 2 here, is non-negative as a matrix, as an infinite matrix, therefore it is non-negative. So once we know that this functional calculus is non-negative on polynomials, how do we construct the integral, the spectral measure? We extend, we evaluate on some vectors, and we extend this to more general functions. And here, maybe I should mention, because in one of my previous lectures, we exploited this idea. So this functional calculus now from the algebra of polynomials to operators is additive, multiplicative, but it's also positive. And now we take, let's say, the continuous functions on R with polynomial growth, and we want to extend this functional to this space.
So what are the continuous functions on R?
Continuous with polynomial growth. Will not be necessary because this is a bounded operator in the end. And the question is, how do we extend this? Well, is the construction of the integral. Fix a vector u and look at this functional. Let's denote it somehow. L, which depends on A, and u apply to P. Now this is a number. Linear, positive. So, as you know, the construction of the integral allows you step by step to add a non-polynomial function and to assign a value and so on using the monotonicity, and in the end you are able to extend this linear functional to one which is defined on all functions of why polynomial grow, because I want to majorize, minorize this function by polynomials to be able to, you remember if you were here, the Riesz extension lemma. Once we have this, or rather R here, we can get rid of the vector u. We remark that this is a quadratic form. We polarize it, and with the standard evaluations, we'll end up with the representation of A as the integral of a spectral parameter what we call the spectral measure on the support of A. This is the path advocated by F. Riesz. And all his life, he wrote articles. He was the first to promote this, to propose this way of defining the spectral measure. And then you can extend it to commuting operators and so on. This is not, I want to insist here, this is not the way you learn and we teach today the spectral theorem in functional analysis. And it's very unfortunate because it is much more natural than what today you do Banach algebras and, I don't know, Gelfand transformers. So you don't need that. You simply need this fact. And what I mentioned, we have the representation with all the properties of the spectral measure as you know. So already this is a highly non-trivial application, and we link algebraic positivity to very analytic one. Now, let's change the support. We are on the unit circle. What happens with a trigonometric polynomial which is non-negative on the unit circle? Same thing, you isolate the roots. I'll not do the proof, it's a simple exercise now. And you remark that the roots which are not on the circle are symmetric, Schwarz symmetry with respect to the circle. And once you combine all this, you get without pain that this is a sum of squares. As a matter of fact, is one single square on the circle. We do the same game, start with a unitary transformation in a Hilbert space. Because you have this decomposition, automatically the functional calculus with trigonometric polynomials now on the unitary is positive. And then you can extend it and you have a full spectral measure. So this is the way Riesz and his school did the spectral theorem. Have a look into the functional analysis book of Riesz and Nagy. They take the time to explain in full detail all the steps how to build the spectral measure from this algebraic fact. And I think it pays back if you follow their approach, because one instance you will see today has many interesting ramifications, this observation. And from here you derive many interesting inequalities. Just for your information, the Fayer's inequality gives you a bound on the coefficient P1 of a trigonometric polynomial which is non-negative. And this is sharp. There are many such applications. But I want to mention another one. If Riesz remains on the board with the following well-known and famous formula. let's take a non-negative harmonic polynomial in the unit disk. So as we know, is the real part of a complex polynomial. And the question is, can we recover only from this part, so not the full polynomials, only the real part, can we recover everything? Well, you play a little with Cauchy's formula, you reflect in the boundary, and you will see that this can be done. That's the observation of Ries and Herlotz. And it goes quite far, because now you can approximate more general functions. You take all harmonic functions which have non-negative real part in the disk, and you will obtain a representation of this form. What it is very special here, the measure which appears in this representation is non-negative. So you have the arc length and the real part of the polynomial, which is non-negative. So here is a non-negative measure. Pass to limit, weak star limit, and you will get a representation for all non-negative harmonic functions in the disk this way. Highly non-trivial. In particular, if you polarize this and you look at this kernel in Z and W bar, you remark immediately that this is positive definite. Why? Because we average here with respect to a positive measure, a product, a square if you want, but a square in the sense of kernels. So it's a kernel function, U is fixed, time is polarized. And here is exactly what Hilbert was doing early on. We have, from this polynomial, we have constructed what we call a positive definite kernel as this average, as this limit of sums of these simple fractions. So, non-trivial observation, go on the diagonal, multiply with the denominator here, and you will see that you will obtain such an impossible representation. Of course, on the boundary, this doesn't converge, but inside, you have the polynomial, which is non-negative in the disk, as the equation of the disk times the sums of squares. So we call it a weighted sums of squares decomposition. Of course, this can be approximated with a finite sum, and it is in the closure of this convex core. So it's something of this form. Now, speaking about positive harmonic functions, we have to mention the founders of the theory. Stiltius, in particular, studied this from the point of view of continued fractions. Then Isai Schur has several observations, and in particular this one, which is also a continued fraction, very useful. And Van Lina put this in the upper half plane. So all of them started with the observation that if you have analyticity plus some uniform bound, or positivity assumption in this sense, you obtain a decomposition into a squares, or as they started at the beginning, Stiltius and Schur, a continued fraction which has positive coefficients. So the positivity is encoded now not in the squares, but in the coefficients of the continued fraction. And this was a major discovery. I spoke about this in one of the seminars last week, and leads to the so-called Schur parameters and the parametrization of all analytic functions from the disk to the disk. This solves the bounded interpolation problem in a very constructive way. And just to give you an idea, if this function, now for the connoisseurs, is not a Blaschke product, is not, let's say, is rational, but not Möbius transform times another Möbius transform, the continued fraction will continue eternally. So this stops if and only if the function is a Blaschke product. So far, we saw this interplay between positivity assumptions and decomposition in continued fractions, which can be put into sums of squares. The typical, and I should have mentioned this very early, the typical lemma, which is of much exploited today, goes back to Kolmogorov to see his studies of stationary processes. If you have an arbitrary positive definite kernel, meaning that any principal matrix selected from here is positive semi-definite, there exists a Hilbert space, and the factorization of this as a correlation matrix of a map with values in the Hilbert space. So the Hilbert space comes automatically from the positivity of the matrix. And we know many instances, geometric instances, where positivity of a matrix is important, and all of a sudden you have the Hilbert space factorization, which brings the geometry of Hilbert space and so on with powerful insight, geometric insight. The problem of Hilbert was solved by Artin and Schreier, and they develop almost from scratch the theory of real fields, where by definition the squares are universally positive, and every odd degree polynomial has a root. So that's somehow the completeness of the field. And by adding the imaginary root of -1, you get something bigger. That means -1 is not non-negative. They were able to solve completely the problem of Hilbert, showing that indeed every non-negative polynomial is a sum of squares of rational functions. And that's, I turn the page now, and that's the beginning of real algebra with a lot of interesting and powerful theorems. For us, what is interesting that the idea, somehow the hint comes from study of geometry, from the foundations of geometry by Hilbert. And I stress that sums of squares are universally positive in this situation. That's quite interesting that every ordered field admits a real closure. So it can go to its real closure. Without doing, very important here, topology. So there are no Dedekind cuts, there is no metric, there is nothing, it's just order. What is behind all this? The old and well-known Sturm algorithm of deciding how many roots a polynomial has. So at the foundation of the whole theory is the so-called Sturm pair. It applies to pairs of polynomials, not necessarily the derivative and the polynomial, which, as you know, it goes as follows. You start the Euclidean division, and you end up with either an exact derivative or a constant. You look along this Euclidean division at the sign changes in the sequence, and just the number of roots pops up from this counting number. It's pure genius. And from here, Tarski, a few years after Artin and Schreier, was able to obtain at the level of mathematical logic the following striking statement. So let's read it together. We are in the first order logic with additivity and order, and the variables are in a real closed field. That means complete in the sense of Artin. Then we can effectively associate to any formula which contains quantifiers an equivalent formula in this logic. So one more time, we allow real variables, which doesn't have quantifiers at all. And moreover, the logical equivalence, the deduction from one to the other, is rather canonical and involves only the Sturm separation of roots method. So that was Tarski. I'll give you the year in a second. So he gave lectures in Poland in 27, announced very short notice in 31, published in 1931. Then he emigrated to the United States. The full details were kept by Rand Corporation over the years of the war and way after. And the full proof came to the public only in 67. There is a shorter account by Zeidenberg, and it entered rather late into the circuit of mathematics. So I want to make a comment here. Hilbert was very fond towards the end of his life at axiomatizing geometry, algebra. He tried analysis, mathematical physics. And he wanted to obtain a complete system, logical systems, which, of course, incorporate these branches. When Gödel came with the observation that if you do logic with numbers, with natural numbers as variables, this was a big blow to Hilbert program. So it's incomplete. You cannot decide. What Tarski did is the opposite. Okay, if you allow real numbers or elements in a complete real field, everything is decidable. Every simple logical proposition is decidable whether it is true or false. And this is remarkable. Puzzling, I don't think is taught in normal curriculum in schools, and it's unfortunate because this should be known widely. It goes opposite, perpendicular to Gödel, and as you will see very soon, is very powerful. So let me give you an example, the simplest possible. Actually, probably it is on my, I forgot. Probably it is on my slides. So anyway, quadratic forms, elementary algebra. The quadratic function is non-negative on the whole axis. How do we decide this? Of course, we can check point by point, But I claim that you know very well that there is a discriminant here. And if this discriminant is less or equal than 0, then we have it. What is this? This contains a quantifier. This is a statement which doesn't have any quantifier and has the variables which are in the proposition. So that's exactly what Tarski does. You eliminate the quantifier and you find a certificate which is in the end equivalent to this statement over the reals. So the applications came late, as I mentioned. One of the most interesting and useful ones is Hermander's inequality. He used this for characterizing hypoellipticity for linear PDEs, and it gives you how fast a polynomial grows outside the 0 set in the real domain. So, and it is always bounded from below by a distance to the 0 set and the power here. Not trivial over the reals. And this leads to the Loyashevich inequality. Maybe you know this in its terms is the root of division of distributions by polynomials, existence of fundamental solution, and so on. So it's quite useful, this fact, for linear PDEs. So in practice, how it is known, Tarski's principle, you take such a semi-algebraic set. This is called the basic semi-algebraic set, given by a number of equalities, inequalities. And you project it. That means, of course, there are some quantifiers when you project. You take only 2 variables out of 3. There exists a point in the fiber which satisfies this. Well, the projection also is semi-algebraic. Non-trivial over the reals. Here it is what I wanted to say. And again, we obtain this fact by completing squares, as you well know. And there are very similar root separation criteria for polynomials in different situations, not necessarily real now, by Ruth, Hurwitz, and so on. The early references, so people started to understand what is going on. So we have fields with order relation. There are also rings, there are algebras, and these are some of the early papers in that direction. I want to pay attention a little and point out this contribution of Stengler, which makes effective Tarski's principle. So let's take some time to see what Stengler has to say. Side remark, in algebraic geometry, you have an interplay between ideals and varieties, defined as zeros or more general supporting structural sheaf and so on. When you work with an order, besides ideals, you have some convex sets, the elements which are non-negative on a set. It's a convex set rather than an ideal. And also the multiplicative monoids play a role. So it's not surprising, and I'll keep this notation, to work not only with ideals, but with the convex semi-ring generated by sums of squares and some coefficients. So anyway, here it is. I want to decide, so I underline decide, whether this system of relations over the reals, or a real closed field, doesn't have solution. Equality, non-equality, greater or equal than 0. So this set is empty, of X satisfying this, if and only if there are elements in the ideal generated by the 0 set. That's quite natural. That's like basic algebraic geometry, the ideal. B is in the monoid, so we are allowed to multiply any of these functions and they remain non-negative. So any product of them is not 0, sorry. And we call it the pre-order generated by H. That means not only the functions which are non-negative, but times sums of squares, they remain non-negative, and sums of them. So this is empty if and only if there exists an element in the ideal which cannot be written as a square of the monoid plus an element in the pre-order generated by this element.
Could you just remind us the definitions of pi g and ph?
Yeah, it's, we'll have some examples. I want to take the time.
I is the ideal, I understand.
Yeah.
This is the multiple monoid with 1.
So the ideal, pi is the monoid,
So AI is the element of
and this is the convex semi-ring generated by this sums.
Yeah,
Okay? Let's take some examples. Let's look at the Hilbert question. Take a polynomial which is non-negative on the full Rn. What means that is non-negative? That the set where it is non-zero and is non-positive is empty. So we have a generator of the monoid and a generator of the semi-ring. What is the conclusion? There exists an element in the multiplier here. Oh, sorry. There exists an element in the multiplicative structure, that means B, and an element C, which is a sum of squares minus P, a sum of squares, so that this is 0. So let's do the computation. P is a sum of squares of rational functions. Let's do this together. Suppose that G equals 0 implies F equals 0. Polynomials in Euclidean space. G of x, I mean. What does it mean? That the system G of x is 0 and f of x is not 0. Has empty solution. So what does it mean? I'll put it on the blackboard. Something in the ideal generated by G is on the right, is 2, we have f equals non-zero. We have f to an even power. And here, of course, always I can add one different than 0, which will give me a sum of squares. Now, if you know the Hilbert non-Stellensatz over the complex field, this part doesn't appear. And here you have some power. So that's the difference. That's the real non-Stellensatz. And there are some other examples. We'll take a break at a certain point. I'll see when is natural. If you allow me, I'll stop at a natural point. So, but we can do better. And the interesting part that if we exploit the spectral theorem, we can obtain better results than Stengler or the general Tarski conclusion. And this was remarked rather late. Gilles Cassier did it for coming from the dual perspective, from the moment problem. Then Konrad Schmidgren and myself, we completed it, and the conclusion is quite surprising. It's much stronger than Stengler, and says the following. Suppose we have a compact set given by a number of polynomial inequalities, and at least one is strictly negative at infinity. For instance, is 1 minus or a constant minus a square. Then any polynomial which is strictly positive on this set can be decomposed as a sum of squares plus the defining polynomials. So that's much stronger than what we obtained from Tarski directly. There is an algebraic proof now and a lot of applications. I'll show you after the break. And what is interesting is the proof here, and I want to finish with this.
Sorry, so Pi is a non-negative on S, but P1 is non-negative, is negative at infinity.
Yes, yeah, there is a stronger condition there, so I'll not go into the details. Proof. Assume that it is not so. This potential space where the polynomial lives is a convex cone. Minkowski separation lemma or theorem gives you a linear functional. The element is not there, which separates the cone from the element. This cone has to have inner points which have to do with exactly such an element. Was so-called Archimedean property. This linear functional is non-negative on sum of squares. I can define an inner product. Is non-negative definite, complete to a Hilbert space. And I remark that the multiplication with the variables are self-adjoint there. Now, the Van...
Space means you integrate against a measure. What?
So I'll get a measure very soon. So, but I have several. They commute strongly. They are bounded by the assumption. Therefore, I have a spectral measure, a joint spectral measure. So I go here a little fast over just the details of the spectral theorem. Once you have this, it means that the functional can be represented by a measure. But once the functional is represented by a measure, cannot be the spectrum, the support is compact, or S, cannot be that the function is strictly positive, the measure is not trivial, and this is strictly negative. We are done. So that's how the spectral theorem, we obtain the spectral theorem with sums of squares, and it pays back and gives you something better than the sums of squares. So, couple of remarks and we take a break. There are quite a few very good texts. If you are interested in algorithmic aspects, starting with Tarski and so on, there are more and more refined, telling you how many squares you need, what is the degree count, and so on. Then there is this fundamental real algebraic geometry treatise, which is quite old now. For positive polynomials, we have a quite recent book which contains much more material than I mentioned here, in particular the mathematical logic background, which is quite interesting, a la model theory and so on. It happens, coincidence, my friend Klaus Scheiderer told me that his book appeared today. I was in touch with him, I was commenting, and today I'm happy. You see, there is another font here, I just added quickly. It contains 350 exercises and is a very friendly, very authoritative exposition of real algebraic geometry from the point of view of sums of squares, so I highly recommend this. What about we take a break now? Welcome back. So you had a glimpse on real algebraic geometry and how the spectral theorem goes back and improves a little the conclusions. There are now just a few examples to finish. Good curves where every regular element is a sum of squares. I'll not go into this detail, just for your information. And the enumerative geometry side, starting with Hilbert, is still very active. There are people who care how many different representations a respective polynomial has and so on. Should we close because of the mosquitoes? I apologize.
Have the circulation.
Oh, okay. It's better there. So watch carefully. What I want to point out is an early observation of Bochner and Crane, Mark Crane, 1940, 1941, so when the war started. Okay, we saw that polynomials are not good for decomposition into squares and representation by positive measures. On the circle they are. So what they remarked, Crane first and then Bochner completed, is that if you have a homogeneous space, topological homogeneous space with a group acting on it, and you consider the so-called harmonic polynomials, these are absolute continuous functions, for instance, on the real line, or they are really spherical harmonics on the sphere, it's a homogeneous space, or elements which have a finite dimensional orbit when you act with a group. They have this remarkable property that the algebraic positivity of a functional, I call it algebraic because you check it only on the squares of harmonic polynomials, automatically implies that there exists a positive representing measure. So this is quite remarkable, it's not widely known, and it shows that probably we do the wrong thing when we work with power moments. Working with almost periodic functions would be much more beneficial. Just a little food for thought. Now, applications. I'll start here, a long list of applications. I'll not go in details in none of them, just showing you what it is good, this certificate of positivity. The simplest observation, which is important for a lot of areas, is how do we compute the global minimum of a polynomial function on a semi-algebraic set. So you have some constraints. You have a quarter of a disk. You have a polynomial. How do you find? Of course, you have Lagrange multipliers. You have convexity properties, but beyond. And the observation is with what we mentioned before. If you can show that this minimum subtracted from the polynomial gives sums of squares. Now I say modulo S, that means with the respective weights, with the respective multipliers, then you win because you have a certificate, so you can write that this is the minimum in a frozen identity as we had at the beginning for the cosine. So that's the whole aim here.
So modulo S means the things whose square you are taking are coming from this?
Let me give you an example. So we have the disk, and we take the upper part. And we have a polynomial p and x, y. And we like to check whether this p star is the minimum. Well, with what I said before, if we add a small epsilon and we make it strictly positive, should be, for sure, a sum of squares plus 1 minus the equation of the distance sum of squares plus y sum of squares. I'll denote sigma squared the sum of squares. Why this is good? Because it's an algebraic identity, and then you can start searching when is this possible, degree by degree. And it turned out that this is very practical, it's very useful, and was implemented by a lot of people, starting with the optimization theory group. The first one who exploited this openly and with a specific purpose was Pablo Parrillo. Now he is a professor at MIT. In his dissertation at Caltech in 2000. So it's a relatively new endeavor here. Immediately after, or almost simultaneously, but with a new idea, Jean-Bernard Lasserre came with the following observation. The same polynomial. Let's denote by S this set. Let's turn to the dual. Let's dualize and look at the minimum of the polynomial P against all probability measures supported by S. Average all of them. This seems very naive and apparently not very good idea. In fact, it is, because you transform this into the moment sequence, as I wrote here. So you consider of course, the minimum will be attained at a point mass, at a single Dirac mass, but you consider all of them. And you work now in the new set of variables, which are the moments of this unknown measure. And the decomposition, which is here, turns out to be just an identity between moments. You write it in terms of moments. And then somehow you linearize the problem. You, of course, accept many more variables. So all these moments are interlaced. They are subject to different constraints. And the method is always convergent and gives, for a small degree and not very complicated sets, and small number of variables, that means in the order of 100. I think it goes now 400, 500, it goes quite well. It converges. This is called the Lasserre relapsation. So look, I show you just with one defining equation. You take the sublevel set of Q and you minimize the polynomial. Now, in the terms of moments, this integral is a linear functional. So that's the point here. I linearize the objective function. And the constraints are simply the moment inequalities, which we know very well. The Hankel matrix has to be non-negative. And the constraint that we are on this set, Q times the sums of squares, has to be non-negative. So the constraints are linear. The objective function is linear. And guess what? You have only to increase the degree, and this will converge. So that's the Lasserre relaxation problem. Now, Pablo originally applied this to dynamical systems. For them, if you have a polynomial vector field and you want to study the stability of the trajectories, of importance is a very useful concept is the Lyapunov function. So it's a function which decreases on trajectories. If you have such a function which decreases on trajectory, automatically you have stability. This ensures stability. And they were able, in his thesis, he was able to apply this to quite a few dynamical systems. I don't give much detail. For instance, like this one, a polynomial vector field. And you can find by this method, almost by hand, the Lyapunov function, which is quite remarkable. Chebyshev-Markov type inequalities. So these are extremal problems in the theory of moments. You want to bound the probability for a certain random variable with unknown distribution, but only a part of the moments known to belong to a certain set or an interval, for instance. That was the Markov original problem. And again, you linearize this a la Lasserre, and you get immediately the classical results of Markov-Chebyshev. So this is new compared to the classical theory. Let's have fun with elementary geometry. Prove that if we have a triangle with sides ABC and area capital A, this impossible inequality, Onos inequality, holds. You will be lost in this proof. And the interesting part is that by taking these non-negative quantities, this come, of course, from the generalized Pythagoras theorem, so they are non-negative. And you introduce, you know, Heron's formula for the area. The inequality turns out to be a sum of squares. Of course, you don't find it easily, but you can search it for low-degree decompositions. And of course, a computer now, a symbolic manipulator, can do that. And if you are lucky, you find it, exactly a la Lasserre relaxation. And the applications go on and on. I'll go rather quickly over some and spend some time on others, and so on. Very classical and important problem in mathematical analysis. You have a sub-level set of, let's say, polynomial or an analytic function, estimate or compute the volume in a given frame, in a disk, for instance. And you turn this into Lasserre relaxation because you simply take how much mass a measure puts on this sub-level set, and you complement this with the Lebesgue measure on the full set and another complementary measure. And this relaxation method with the variables as potential moments works, and it gives you an estimate of the volume. I'll give you references. Much more interesting, maybe for some of you. You want to compute the spectrum of, let's say, a Sturm-Liouville problem or some even PDE operator, and you want to see whether it has negative eigenvalues. Well, that's in general hard, as you know, and you need different tools. There is a group of people, and Handy works in PDEs, Bertsimas in mathematical economics with Karamainis. And the idea is the following: if you can split with denominators, I claim, the PDE, the operator, minus the spectral parameter into a sum of squares, then you have a certificate of positivity. And this operates on some Schrödinger equations. It depends on the potential. And Handy has some interesting observations there. And there are applications to, as I mentioned, to economics from here. So I'll return to this because now you turn into something non-commutative. So far, we had only commuting variables. Of course, the differential operators don't commute. This is why I put one to the left, to the right. And now there is a whole trend to do free-star algebra, to do non-commutative inequalities and all kinds of estimates, as I mentioned, with non-commuting variables. One of them is here. This is Conrad-Schmidgen. We work abstractly in the Weyl algebra, so the commutation relations are, as you know. In the Schrödinger representation, one is multiplication by the variable, the other is derivative. And if an element there has the leading term, so we now take a non-commutative polynomial. We put all p's to the left of the q's. And if the leading term is strictly bounded from below, kind of strong ellipticity, then there exists a universal denominator of the form the Laplacian, minus the Laplacian is positive, plus it's adjoint in this sense, and L, so that this is a sum of squares. This is new and opens the area, what I mentioned before, to study from purely algebraic perspective positivity of differential operators with polynomial coefficients, linear. Real variables are good, but complex are better. And I'll tell you why. In all these computations I mentioned, in all this optimization, you want to represent polynomial with a matrix. In the end, you end up with a matrix. And you write this as A times the tautological vector, as we call it, times another tautological vector. So this is a matrix, and this will be a quadratic form, but evaluated on the tautological vector, which gives you a polynomial. And the whole machinery of optimization uses this representation because in the end, our customers want matrices rather than anything else. Matrices are superior. The trouble with this representation is that A is not unique. You can have identities which give you 0. If you do the representation over the complex field with Hermitian forms, or Z even, this comes with a, now this is over R, this is over C, a big difference. This comes with a conjugate. This is unique. So you can recover from this polarization the matrix B. So there is a big difference between the complex, one of them, which for practical purposes is quite important. So let's work with Hermitian sums of squares. Of course, these are universally positive, but they are less. They are, for instance, simple exercise, you take the Laplace operator of this and it will be non-negative, while here it can have any sign. And here comes Quillen in the direction of Crane and Bochner. On the sphere in Hermitian space, every positive polynomial is a sum of Hermitian squares. So I can write a polynomial not as a sum of squares, as we discussed, on this algebraic variety, homogeneous by the way, but as a sum of Hermitian squares. So that was rather surprising. And the proof was by quantization, by going to the Toeplitz operator associated to this form in the Fock space. I'll not go into the details, use ellipticity, and in the end obtain the respective decomposition. So it was a little indirect and using the whole machinery of spectral analysis on Fock space. And there are many applications here. One of them I want to mention because Atavale comes from this country. His contributions in the early 80s was the following. Okay, if we have this decomposition, we apply this to a commuting system of operators satisfying the equation of the sphere. Then automatically we have the positivity of the functional calculus. We put all the stars to the left. As we discussed before, we obtain a representing measure. We call this T subnormal. It has a normal extension to a bigger space. And this is quite surprising. If you know, for instance, maybe you know for a single operator, if T star T is the identity, what is this? An isometry. An isometry subnormal can be extended to a normal operator. So can be represented with a spectral measure on a bigger space. Well, this is true because of Quillen property on the sphere. And the question is, what happens on other boundaries? So take an arbitrary compact real algebraic variety in Hermitian space and ask the same question. And the following are equivalent. This is a fact I proved a few years ago with Klaus Scheiderer, the author of the book I was advertising before. Every polynomial strictly positive on that compact real algebraic variety is modulo the ideal sum of Hermitian squares. This is a universal subnormality certificate for operators annihilated by the ideals, so what we had before. Go to normal matrices and a very specific condition of the polarization of this in the complex domain of the ideal. So the main result, and here I wanted to arrive, you have the Quillen phenomenon if and only if the equation of the sphere is in the ideal plus a sum of Hermitian squares. So you cannot expect to have a strictly positive polynomial, a sum of Hermitian squares on this variety, unless the equation of the sphere is embedded there. So you can add it there, and you say, okay, so this is a pullback of the sphere by some algebraic map. some rational map. I'll not go into much of the proofs, but this answers a question of Kathleen and D'Angelo. These are important names in several complex variables raised in the 90s. They ask, okay, the sphere has this equivalent property. Are there other strictly pseudo-convex boundaries on which this is true? And the answer is not necessarily. And from here, there is a Hermitian complexity index, which tells you when the Quillen phenomenon holds. And there is an interesting observation here that if an ideal has this infinite Hermitian complexity, automatically the boundary contains an analytic disk embedded into that. So there is a stratification of conditions which depart from the Quillen phenomenon, and at the very end of it, at the limit, we go to infinity, you have an embedded disk. And obviously there is not possible. Turn the page. Delay systems. Why we are interested in delay systems? Usually the response of in a dynamical system when you do control is instantaneous. But when you deal with biological systems, for instance, the response has a delay. And for that reason is one of the most important parts of control theory to assure stability of dynamics, maybe with a controller embedded, when you have a delay. And the delay enters into the time like this, with a vector and so on. And very interesting that the stability is governed by the location of the zeros of the characteristic function. So you take the Laplace transform, and the interesting part is you mix, when you have delay, the variables with the exponentials. Obviously, the Laplace transform will take this into exponentials, and the derivative will be multiplication by the variable. So when you have this mixture, it becomes very hard, and there are only partial results, much less is known. It's a wide open area of research to study sums of squares decompositions involving monomials and almost periodic functions. And if you reduce this to a torus, you have a condition like this, which is indeed the sums of squares, but with some denominator. Here I want to spend a little time without giving you too much technical detail. It's a part of work I did with a couple of colleagues on the construction of wavelet frames. So what is a wavelet? It's a shape which can be decomposed into a finite sum of stretching. So you can multiply with a number, or you can dilate the domain, the time. And this shape can be written as a finite sum of this stretching. This is written in condensed form like this. So this is the mother wavelet, and these are the stretching. There is a transformation, a rotation U, and translation. Don't bother about the details. You go in the Fourier domain, and this will become the so-called refinable function. So it's a trigonometric polynomial now, but in higher variables. So you live on a torus on several variables. And the algebraic properties of this polynomial, so after you take the Fourier transform, gives you full account on the construction of wavelength string. So finding different shapes which have this property is extremely important for applications. So there are some technical conditions here, and you normalize this refining function to be one, to be the identity is a matrix at 1 at the corner. And if you have such a decomposition, automatically the original family of functions can be extended to a tight wavelength frame. And then you can decompose functions into this frame as you decompose into trigonometric polynomials, and they somehow reflect the geometry of the domain. So what I wanted to show you is that it's a sums of squares decomposition here in the matrix valued case on the torus, which gives you the whole construction. So very slowly I passed from scalar to matrix valued. And this is the situation. Unfortunately, it works only in 2 variables. So dimension 2 is very special. And there, if you have these conditions, there are polynomials which complete the difference between the identity and this matrix, and it gives you a sums of squares. Speaking about the matrix situation, matrices don't commute. So you want to study positivity. And then the standard setting is rather than looking at the polynomial ring, you consider over R or C variables, they're adjoined, finitely many, with the property of the adjoint that, as you imagine, this reverses the order, and you postulate that this is the universal square. So this is the square, that means this is non-negative. This started about 20 years ago, is now in a full bloom, and there is a very interesting result of Bill Helton. Saying that if you have an element here which evaluated on all possible matrices in a given order, of course, this is order fractional calculus, is non-negative in the sense of matrices for all matrices, then F is a sum of squares. Very simpler in some sense and straightforward compared to the commutative situation. So the non-commutative setting is much simpler. Any star polynomial which evaluated on matrices on all sizes is non-negative, all sizes is non-negative, is a sum of squares. And then convexity means essential linearity here and so on. And it goes, there is now a whole machinery. I'll not go into much detail on that, but I wanted to mention this.
So you do it for all n, right?
But for all, no, n is fixed, but A, J are matrices of side D times D, and D is arbitrary. So let me finish with this statement of Tarski. By a decision method for a class K of sentences is meant a method by means of which, given any sentence, one can always decide in finite number of steps whether theta is in K or not. And the importance was stressed by Hilbert, who considered this as a main task of new field of mathematical research called metamathematics. Now, I invite you to read the introduction to Tarski's memoir published by Rand. Now it's on the web, and see the other logical systems which satisfy this. There are quite a few. Contrary to Gödel's incompleteness result. Before we finish, okay, we discuss about some negative results, impossibility of decomposing a non-negative polynomial into sums of squares. Here are two examples. They came in the 60s, so 80 years after Hilbert. And I invite you to prove by hand that this Motzkin polynomial is not a sum of squares. So you have to chase, it's degree 6. You have to chase the leading term, and then you go to the value at origin, you factor something, and you will see it's quite fun. It is a good exercise, and you have to know it. It's a part of, I would say, folklore, and has to enter into the circuit of all mathematicians. This example of Robinson is not that easy to show. It's also degree 6. There is a whole book of Bruce Resnick, which I recommend, sums of even powers of forms, which contains long discussion of this. And what is interesting in these two examples is that they are of the form they are in two variables, so it's cosine square 2 theta p r square plus sine square 2 theta q of r square, where p and q are non-negative polynomials on the line. So if you pass to polar coordinates, you will see rather quickly that they are non-negative. But the interesting part is in polar coordinates, they are sums of squares. Of course, adding the harmonics, the trigonometric part, but as monomials, they are not. So I'll show you my collaborators, and then I'll make some comments. More recent references for the applications. This has exploded. Now it's way too big to cover in one lecture. This semi-definite conic polynomial optimization is a handbook which contains ample articles on the optimization method of Lasserre. Then Jean-Bernard has quite a few books. Look at the early one. The more recent ones go into PDEs, into more sophisticated things. And there is a collection of articles, semi-definite optimization and convex algebraic geometry, edited by Greg Bleckerman, Pablo Parillo, Reka Thomas, and much more. So what are the main issues today? How many squares you need, bounds on the degree of the polynomial. For the positive Stellensatz I mentioned at the beginning, sorry to disappoint you, the degree depends doubly exponential on the degrees of the variables, of the elements. So it's not a very good news, but on the other hand, in practice, turns out to be better, and nobody has an idea. Then, what is the gap between positive polynomials and sums of squares of polynomials? You take these convex cones, they are both convex cones, you cut them with a transversal affine place, and you compute the volume. Well, the volume shows that there are many more, not only a few found here, many more as the dimension increases than you would expect. And so on. There are, of course, computational aspects, how much computational power you need to do the optimization. I'll not go into these details. The software, to my knowledge, possibly is in other places. The Toulouse people have it here. And I think it's a free software. You can play with it. And if you have a minimization problem of polynomials, don't hesitate to use it. And also the Caltech group, the control theory group, has this one. My collaborators, the closest to this field. This is Bill Helton. Maria Karina is no more among us, very sadly. Jean-Bernard Lasserre and Klaus Scheiderer. Thank you very much.
Questions?
Any interesting problem where you don't know the solution?
The most important problem. Well, depends.
Interesting, simple looking problems.
Oh, the most interesting, in my opinion, is the Weil algebra. The Weil algebra to study in detail, because this will explain D-module theory, will explain PDEs, will go into deep waters, and unfortunately, people go to the extremes, either commutative or free. And I think the Weil algebra is the most interesting, in my opinion. But there is little work. I would like to see the connection, because there are some, how to say, modest results. The connection with D modules, for instance. And this doesn't exist yet. But if you ask an engineer, it will tell you a different story, a different problem.
I want mathematics.
Okay.
I have a question.
Yes, please.
You talked about polynomials which are sums of squares, and of course, you mentioned these form sort of convex cones.
Yes.
But in addition, especially if you look at positive polynomials, they not only form a convex cone, they form a closed convex cone. Which means on this side also we should be talking also about limiting sums of squares.
Oh, yes. Well, you enter into all this discussion with there is a
A countable sum of squares.
yes, and
polynomial.
that's Hilbert space decomposition. That's a kernel decomposition. A positive definite kernel is a sum of countable squares. So you enter with this exactly into positivity of kernels. So when you accept countable sums of squares, it's a positivity as a kernel, rather than algebraic. So your question exactly, what is the boundary between algebraic, my title, and analytic?
There are none. Thank Mihai again.
Thank you.
Okay, I guess we should have high tea upstairs. So many areas to apply.
Yeah.
Huge. The reason I remember limiting is because in our paper we
Yes.
in 2022 we did that. We needed an integration trick for the
I know.
moment thing.
I know. Well, Hilbert did it for the worrying problem. He wrote an integral.
Limited. Okay.
An integral is a limit.
So even if we are to do
An integral is a limit.
that's right.
Yeah.
That's right.